In the last part of this module, we're going to look at colligative properties. And whether you know it or not, everyone's taken advantage of colligative properties at some point in their life. Colligative properties, they're important because they're something that can be changed just by the addition of an impurity, by the addition of a solute to a solvent. And the important aspect of colligative properties is it does not matter, it does not depend on the identity of the impurity. It just depends on how many of those impurities did you put in that solution. So colligative properties can be changed by the addition of a solute, which is basically, right, we're adding something foreign to a solvent. And the important thing is it does not depend on the identity. Does not depend on the identity of the solute, right, on the impurity. It just depends on how much was added. Molecules or ions in solution. And we'll take a look at what this means exactly. And so examples of colligative properties, we can influence something's melting point by changing its purity. We can influence something's boiling point. And we're going to focus on melting point and boiling point. We're not going to talk about osmotic pressure, but that's the other thing that can be influenced by changing the colligative properties, by changing the purity of a sample, by introducing something foreign into that solution. So we're going to look at how we can take advantage of colligative properties to influence something's melting point and something's boiling point. And so the way to think about colligative properties is I have this solution, and it's at equilibrium between what is in the liquid phase and what's in the gas phase. And to have something that's at equilibrium, it means, right, as one of these molecules evaporates and goes into the gas phase, that means another one of these molecules condenses and is going back into the liquid phase. So to that system at equilibrium, I add this impurity, right? I add a non-volatile solute like sodium chloride. So, right, here's my water. I'm making pasta, and then to that water, I sprinkle in some salt. Right, that salt is an impurity. Those salt particles, they ionize and give me sodium cations and chloride anions. And what happens is I replace those dipole-dipole and hydrogen bonding forces within that solution of water. I now form new intermolecular forces between the water and the ions that are in solution. And what that does is it decreases the propensity now of my water. It decreases how much water can go up into the vapor phase. It actually keeps more in solution. And so we're going to establish a new equilibrium where now I've got a lower concentration of my sample in the gas phase. So I've added an impurity to that, and by adding an impurity, I decrease the vapor pressure. And an important way to think about what's happening here is we need to reintroduce the definition of boiling point. Right, my boiling point is the temperature where the vapor pressure equals atmospheric pressure. And my vapor pressure is essentially how many molecules do I have in the vapor phase pushing down on my solution. So more molecules in the vapor phase, the higher the vapor pressure. And that means, right, so what I've seen here is a decrease in the vapor pressure because I go and I decrease the number of molecules in the vapor phase. And what that does is it increases the boiling point, right? Vapor pressure and boiling point are inversely related. So I've seen a decrease in vapor pressure, and that results in an increase in boiling point, because boiling point is the temperature where the vapor pressure equals the atmospheric pressure. So by adding the sodium chloride into this solution, by adding these sodium chloride ions into solution, I've decreased the vapor pressure. Now I have to actually heat the sample up even further so that the vapor pressure equals the atmospheric pressure, right? I made those two farther apart. I made the vapor pressure farther apart from the atmospheric pressure, which means I have to put more energy in to reach that vapor pressure equilibrium with my atmospheric pressure. I've decreased the boiling point as a result of that. So let's just take a look at the boiling point change first. So we add that solute. Adding the solute lowers the vapor pressure, and that increases the boiling point of the solution. And so at this point, everyone is probably thinking, well, I add salt to water when I'm making pasta because it boils faster. No, that's not true. Actually, you're adding that salt to the water and you're increasing the boiling point of that water. So it's actually going to take a little bit longer to boil, but what it does is it means I'm going to have a boiling point at a slightly higher temperature, and I'll cook that pasta a little bit faster because I'm boiling at a little bit higher temperature than I was otherwise. So we add that impurity, we add that solute to solution. It increases the boiling point by decreasing vapor pressure. And so here's my original boiling point. I add that impurity. Here's my new boiling point. Right at 1 atm pressure, I'm going to have to heat that sample a little bit higher, right, to now reach that boiling point. So with the colligative properties, we observe boiling point elevation. So my boiling point will always get higher if I add an impurity to that solution. If I add an impurity to that solvent, I'm going to see an increase in the boiling point. The opposite is true for the freezing point, right? I decrease now when I add that impurity. I've decreased the vapor pressure, and by decreasing the vapor pressure, now I've got a freezing point depression. The freezing point actually gets lower. And so this example, right, here's my original freezing point. I add that impurity. So if I was water, my original freezing point was 0 degrees Celsius. I add that impurity to it, and that lowers the vapor pressure. And because of that, right, I'm going to have a new freezing point that's somewhere below 0 degrees Celsius. So maybe negative 5 degrees Celsius, depending on the impurity added. So we get boiling point elevation and freezing point depression. This example of freezing point depression, we use this in the winter, especially in Syracuse. This is why we salt our roads, we salt our sidewalks, because by adding that salt to the surface of the road or adding that salt to the surface of the sidewalk, at 0 degrees Celsius, we no longer form ice. Now we have to be at -5 or -10 degrees Celsius to form that ice, because we've now changed that melting point of ice. We've made it harder now to form ice at 0 degrees Celsius. And so that makes it easier for us to keep the roads clear and to keep the sidewalks free of ice. So we can determine the change in the boiling point or the change in the freezing point for any solute, any solvent combination. All we need to know is this Van Hoff factor that I'll talk about in a little bit, and the molality of the solution. That's why we introduced molality earlier today. And we can find what is the change in that temperature of the freezing point or the boiling point. What's the boiling point elevation or the freezing point depression? The only changes in these calculations are that for my freezing point, it's a depression, so we're subtracting that value, and I'm either going to use my boiling point constant or my freezing point constant, depending on what form of the calculation I'm doing. And we can see those constants change for the solvent that we're talking about. So for water, the boiling point constant is 0.51 degrees Celsius per molal, and the freezing point constant is 1.86 degrees Celsius per molal. Right? I would give you these numbers. I don't expect you to memorize these numbers. What you definitely should know, you should know the normal boiling point and the normal freezing point of water. If I gave you any of these other samples, right, I would provide any other boiling point or freezing point. I wouldn't expect you to know those. But for water, you should definitely know the boiling point or the freezing point. And if we're given a calculation where we need to find our change, if we given those temperatures and we have to find the change in that temperature of the boiling point or freezing point, it's always the temperature of the boiling point of the solution minus the solvent, or the temperature of the freezing point of the solution minus that of the solvent, where the solution, remember, is the mix. The solution is the impurity mixed together with the solvent. So in that previous slide, I talked about the Van Hoff factor, right? I talked about how my change in my boiling point equals Van Hoff factor times the boiling point constant times the molality of that sample. I is my Van Hoff factor, and I is very important because it takes into account how many molecules or ions are in solution. And that's really important because the Van Hoff factor, like I said, this calculation, this colligative property, it does not depend on the identity. It depends on how many things that I have in solution. And so as an example, sodium chloride. Sodium chloride solid ionizes in solution to give me sodium +1, chloride -1. That Van Hoff factor is 2 because I get two different things in solution. I get a sodium ion and I get a chloride ion. The Van Hoff factor for calcium chloride, you get calcium 2+ in solution plus 2 chlorides in solution. Right now I have 3 different ions, 3 separate ions in solution. My Van Hoff factor is 3. So that's the importance of the Van Hoff factor. That's the importance of these colligative properties depending on how many things I have in solution and not on the identity of what I have in solution. And the last example would be something like glucose, C6H12O6 solid. Sure, it's soluble in solution, but it's a molecular compound, so it goes into solution as a molecule. It does not ionize. And that Van Hoff factor would be 1, because I only have one thing in solution. I have one molecule of glucose in solution. So for anything that's ionic, we need to figure out how many ions we have in solution. For anything that's molecular, the Van Hoff factor would always be 1. So now here's a good question. Why is calcium chloride better at melting ice than sodium chloride? Right, our calculation would be my change in my freezing point equals a negative Van Hoff factor times my freezing point constant times my molality. So why do we use road salt that's calcium chloride and not sodium chloride? Why do we use calcium chloride in the winter and not sodium chloride? Well, the answer is because calcium chloride has a larger Van Hoff factor, right? Calcium chloride has a larger Van Hoff factor. And and that'll result in a larger impact on the freezing point depression of ice. Right, looking at this calculation, all things being the same, right, if I'm dealing with a sample of ice, my freezing point constant's the same. If I have equal molalities, right, if my concentration is equal, for calcium chloride, my Van Hoff factor is 3. For sodium chloride, my Van Hoff factor is 2. So I'm either going to multiply by 2 or I'm going to multiply by 3, right? Obviously 3 is larger, so I'd expect to see a larger impact on the boiling point depression if I was using calcium chloride than I was using sodium chloride. And even better yet, let's say, we had something like aluminum chloride, right? Now we're getting aluminum 3+ and 3 separate chlorides. That would be even better than calcium chloride because I'm going to have a Van Hoff factor, right, of 4, an even larger impact on that freezing point depression. So here's a calculation for you. What is the boiling point of a 1.15 molal aqueous solution of sodium chloride? Given that the change in boiling point equals my Van Hoff factor, so I've got sodium chloride, right? That's going to ionize into sodium and chloride. My Van Hoff factor equals 2. So I want to find my boiling point, and that equals my Van Hoff factor of 2. My boiling point constant of water is 0.51 degrees Celsius per molal, and they've already given us the molality of the solution, 1.15 molal. So I multiply those 3 together, and I get approximately 1.173 degrees Celsius, right? When I multiply, molality cancels out and leaves me with degrees Celsius. Here's the trick though, we're not done, because you should be thinking water normally boils at 100 degrees Celsius. I'm looking at 1.17 degrees Celsius. That seems a little bit low. And that is low because this is not the boiling point, that is my change in boiling point. And remember, the change in the boiling point equals the boiling point of my solution minus the boiling point of my solvent. And so here, the boiling point, my change in boiling point is 1.17 degrees Celsius. What's the boiling point of the solution? That is the water and the salt together, minus the boiling point of the solvent, which is 100 degrees Celsius. So to solve for that, I'm going to add, right, 100 degrees across on both sides. And I see that the boiling point of my solution should be 101.17 degrees Celsius equals the boiling point of the solution of the salt and the water together. So there's the catch to those calculations, is that we can't forget that the original sample, the original solvent boiled at 100 degrees, we calculated the change in boiling point to be 1.17 degrees Celsius. So my new boiling point is not 1.17, right? That's way too low for the boiling point of water. My new boiling point is the original boiling point plus that change for 101.17 degrees Celsius. Here's one more calculation for you. So ethylene glycol, it's commonly used in antifreeze, and so you put that in your engine and your radiator in the winter, and it helps prevent that solution in your radiator from freezing and cracking your radiator. So antifreeze, what's the freezing point of an aqueous solution that contains 250 grams of ethylene glycol, given that the molecular weight is 62 grams per mole? And we'll say that the total mass of the solvent, just to make our lives easy, is 1 kilogram. And the freezing constant of water is 1.86 degrees Celsius per molal. So step one, I need to find moles because ultimately I need molality in this solution. Right now, the only thing we know is Van Hoff factor and my freezing point constant. Right, my Van Hoff factor, ethylene glycol is nonmetal, 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 which means it's molecular. Because it's molecular, right, Van Hoff factor equals 1. It goes into solution as a molecule. So step 1, I need to find moles. Well, I have 250 grams of ethylene glycol, and I know ethylene glycol is 62 grams for every 1 mole of ethylene glycol that I have. Grams cancel out, and approximately 4.03 moles of ethylene glycol, and that is in 1 kilogram solvent. So the next step, I want to find my molality. So I have molality, moles over kilograms of solvent. So my molality would be 4.03 moles over 1 kilogram of solvent, giving me a solution that is 4.03 molal, right? Not a hard calculation there, but now we're ready to do our change in freezing point calculation. So my change in freezing point for this would be my negative Van Hoff factor. So 1 is my Van Hoff factor. My freezing point constant, 1.86 degrees Celsius per molal, and the molality of this solution, 4.03 molal. So when I multiply, again, my molality cancels out, and it leaves me with my change in freezing point equals negative 7.5 degrees Celsius. So again, my change in freezing point equals the freezing point of my solution minus the freezing point of my solvent. This one is not a hard calculation because it doesn't change our answer like it did for the boiling point. So I found that the change in freezing point equals negative 7.5 degrees Celsius, right? The freezing point of my solution minus 0 degrees Celsius, which is the freezing point of water of my solvent. So I can add 0 degrees Celsius across, and as you can see, that doesn't change my calculation. So the freezing point of this solution, right, of ethylene glycol, instead of being 0 degrees Celsius and your radiator just cracked and broke because that froze, no, it's negative 7.5 degrees Celsius. The last little bit on solutions are looking at kind of a unique class of solutions. They're known as colloids, and they're basically suspensions. They're cases where the particles that we're looking at, the particles that are the solute, are so incredibly small that they're almost eternally suspended in that solution. So they're not really impacted by gravity to settle out of that solution, and so these really small particles that are dispersed in solution, they stay suspended in solution in the form of these colloidal solutions. And whether you know it or not, we're familiar with a few of them. And so some examples, right, would be fog. Everyone's seen fog. And so we've got something like water vapor, right, dispersed, really small droplets of water dispersed, right, in air. And that's what fog is. We've also looked at smoke, right? Smoke would have, you've got really small particles from that fire that are also dispersed in air. Things like milk as well. You've got more of an emulsion where you have a liquid dispersed in a liquid. And so an example of that would be you have fat in milk, and it's when you homogenize milk, you break that fat up into really incredibly small little droplets of fat, and they're so small that they stay suspended in that solution. So if you've seen unhomogenized milk, right, that unhomogenized milk has gone through a phase separation where you've got the cream on top and you've got a water solution on the bottom. So whether we know it or not, we've all seen a few examples of suspensions. right? Two key examples are that we've definitely seen would be smog or smoke, right? Where you've got really small, fine droplets suspended, and again, they're so small that they stay in that solution for a really long time. They don't really settle out. And so we can see that example here, if you want to call this smog or if you want to call this fog. I'm not quite sure from the picture, but given that's a large city, this could be smog, which would be which is an example of colloids in the sense that all of that particulate matter we're seeing is the product of combustion from fossil fuel engines or combustion from something that's heating your home or making energy in this area. And again, it's going to give off these small particles which stay suspended in the atmosphere for quite a period of time. The interesting thing about these suspensions is that these colloidal solutions, they're able to scatter light. And so the first cuvette here is just pure water. There's nothing in it, and because it's just pure water, the laser travels right through it. But because of the other two solutions in these cuvettes contain a colloidal solution, right? Because I have actual particles dispersed, what happens is that laser light hits these little particles and gets scattered. And because it's scattering that laser light, we can see it with our eye because it's bending some of this laser light in a direction that then, right, travels to our eye and we can see that light because it's hitting these colloidal particles that are suspended in solution. Right, and so here are two examples of the Tyndall effect, whether you knew it or not, right? We can call it the Instagram effect for that matter, right? Everyone's taken an Instagram photo and applied those different filters. Well, here's the natural filter performed as a product of light passing through a colloidal suspension. So here's a foggy morning, and so we've got droplets of water that are suspended in the air. How do we know that? Because when the light coming from the sun through the trees hits those droplets of water, that light is scattered in different directions, and some of those directions, right, lead to our eye, and we see that scattering of the light. The same could be said for a sunset or a sunrise. When we get all of those colors in the sky, it's because of all the dirt and the dust that's along the horizon in the atmosphere. As the light is traveling through the atmosphere, it's traveling through all that dirt and dust that's suspended in the atmosphere, and it gets scattered, and it separates out from all the white light that's all the wavelengths together, and it is scattered and gives us these different regions of different colors based on how the wavelengths of light are scattered. And so we see the oranges and the reds and the purples and the blues because of that scattering. So the main things from today, right, we need to understand from this chapter, from Module 12, that ionic compounds go into solution. They go into solution by overcoming the lattice energy, right? That's why something can go into solution. We need to overcome the lattice energy holding that molecule together as a solid. And so in order to do that, number one, we're going to increase the entropy by mixing two things together, but number two, we need to make stronger ion dipole interactions between the ions in solution and the solvent than the interactions I have, right, the ionic interactions I have in that solid. So solutions form, right, for two reasons. We're increasing the entropy by mixing those things together, and some are also going to be releasing energy as well. To determine if solutions will form, we also have to look at, if we're going to mix two liquids together, right, like dissolves like with respect to polarity. So I would expect two polar solvents to be able to mix together. I would expect a nonpolar solvent and a nonpolar solute to mix together, right? But I would not expect, right, the oil and water example, I've got the really polar water, really nonpolar oil. That does not mix together. That's your salad dressing example where you get the phase separation because you've got drastically different polarities. Gases behave a little bit differently. As pressure increases for a gas, the solubility increases, right? Just think of your cold soda. The second you cap that cold soda, what happens? We go to reach a new equilibrium by carbon dioxide leaving solution. And for ionic compounds in general, as temperature increases, so does the solubility. Temperature for gases has the opposite impact. If they increase the temperature of the solution for a gas, the solubility of that gas actually decreases. And again, think that soda example. Does a soda stay carbonated longer if it's kept in the refrigerator or if it's kept on the counter at room temperature. Our next chapter we're going to start is going to be organic chemistry on Wednesdays, chapter 22.